This is Shuvam Mandal, PhD scholar from CSIR IMMT, Bhubaneswar. I am presenting my work on L10FeNI, tetratinite, rare earth free permanent magnet for the future, on the prestigious Eve platform of behind the teacher's desk. Permanent magnets are used for energy conversion from electrical to mechanical or vice versa. The market is roughly split between neodymium magnets and hard ferrite in 2:1 ratio, whereas their cost is currently between 25:1, which is supposed to increase in higher rates in the near future due to the rare earth crisis and the trade war with China. The research in the permanent magnetic materials is divided into three parts. First is to decrease the content of rare earth elements in the rare earth magnets. Second is to find a gap magnet to fill the BH max gap between the hard ferrites and rare earth magnets. And the third is to replace the rare earth magnets with different materials like L10FeNi and FeCO. We are concerned with L10FeNi. Why L10FeNi is so interesting? It is naturally existing and shows great potential as permanent magnet. Fe and Ni both are earth-abundant materials, and low cost of Fe and Ni leaves space for costlier processing techniques for magnetic materials. What is L10Fe and Ni? L10 is a highly ordered structure where atoms of constituent elements of the alloy occupies alternate planes. As in case of the FeNi shown here, we can see that in FCC FeNi, the positions of Fe and Ni cannot be determined. But in case of L10 ordered, as shown in the three structures below, the alternate planes are occupied by Fe and Ni. In meteorites, L10FeNi is known as tetratinite and is commonly found in two different types. The first equilibrium is called equilibrium state, where the tetratinite is formed at the green boundaries and of disordered FeNi grains due to diffusion of Ni at extremely slow rates through millions of years. Second is metastable phase, where FeNi first reaches the martensitic phase, and due to further extremely slow cooling, the tetratinite is precipitated as nanoparticles in the martensitic matrix. The formation procedure of the two phases are shown in the phase diagram here. Now we will discuss about the challenges of L10FeNi synthesis in laboratory. The main problem in artificial synthesis is extreme slow diffusion of nickel in the lattice around the order disorder temperature of 320 degrees C. It takes 2600 years for one atomic jump of nickel in the lattice at that temperature. Characterization of L10FeNi is also difficult as it cannot be detected by simple XRD or electron diffraction. Synchrotron XRD and gamma ray absorption spectroscopy is generally used to detect L10FeNi. Also, it can be indirectly detected by measuring small changes in thermal, electrical, and magnetic properties. The literature in L10FeNi synthesis shows that it was first synthesized in 1963 by neutron irradiation of single crystal FeNi and later synthesized by electron irradiation in 1979. After the advent of rare earth magnets, the research in the field slowed down and again gained interest around 2012 due to the rare earth crisis. From 2012 to 15, the research was conducted to increase diffusion at low temperature. Later, in 2017 to 19, researchers have tried to chemically synthesize L10FeNi with some exciting results. Our experiments are designed to synthesize FeNi nanoparticle and study the formation kinetics of L10 FeNi fields. Here we have produced FeNi by two different methods, the top-down method and bottom-up method. I have shown in the following slides the data of one top-down method, the mechanical milling, and one bottom-up approach, the sol gel method. We did wet milling of FeNi to form FeNi alloy in the submicron notch. We obtained FeNi alloy, but the shape of the particles were flaky. Also, we found lattice distortion in the alloy. There was also large variation of particle size and composition in the wet mill sample. We did dry milling. Here we obtained particles of more irregular shape than flaky, and distribution was also even than the previous experiments. In the bottom-up approach or sol gel approach, we made a solution of iron and nickel nitrate. Then we added edible gelatin to form a gel, which was then dried to form a aerosol. The aerosol was oxidized at 900 degrees C to form Fe2NiO4, which was further reduced to form FeNi. The reduction of FeNi was carried at different temperatures and found that the optimum temperature for reduction is 800 degrees centigrade. In future, it is aimed to study the magnetic properties of FeNi produced by different processes. We aim to optimize the processing techniques of FeNi nanoparticles and do different thermomechanical treatment to study the kinetics of formation of L10 FeNi. Thank you.